Welcome to this presentation of Limit 2019. My name is Nick Friedl and the topic of the workshop is weld assessment of train structures using aluminum extrusions. So in the next approximately one hour, I will talk about weld generation using profiles, profiles that actually describe extrusions. Then I will demonstrate how we can use the new auto creation method in Limit to define setups based on the topology filtering. I will talk about checking the welds, defining loads, creating jobs. Then we will move to the post-processing, and after that I will demonstrate how to check and modify setups after the first iteration loop, and at the end I will present how to generate a report. Now I mentioned profiles and extrusions. On this slide you can see what is meant by profiles or extrusions. Those are components that usually have longitudinal welds, mainly full penetration welds with backups, so actually high quality welds, and we have developed a certain workflow to deal with these structures or this kind of structures. Now, just to give you an impression what the model of this workshop looks like, it's actually a sub part of a car body, and we generated some loads. In this case, it's a vertical load causing shear forces here in the sidewall, and the second load case actually shows the deformation pattern of the sidewall and the door posts due to a pressure load acting on the sidewall. Okay, so let's move on. Next step is actually to start Limit and to import the model into Limit 2019. So I will use the import and Nastran interface, and I have to use the file browser to move to the example. And we are loading the model. So this will take a few seconds. Here we are. Okay, so that's what the model looks like. And what you can see in the default viewport settings is a color scheme based on the property information that was also imported together with the geometry of the finite element model. So if we inflate the list of sets, we will see that there are some property sets, and each property set refers to an Nastran property ID or refers to an Abacus shell section definition or refers to a ANSYS property ID number. And the basic idea in Limit is to use this property information to generate welds, which means that if we have areas with different properties, or in other words, if we have nodes that here, for example, so if we have nodes that are connected to elements with different properties, then this is a potential position for a weld. And so that's one of the most powerful algorithms within Limit to detect welds is by using this property information. Okay. There is one problem with this approach for these extrusions. I have prepared a set to demonstrate this. So if I, for example, isolate parts of the sidewall, then you can see different properties involved here. And if I run the standard generate weld sets by property algorithm, I will get very many welds or potential weld positions, because we have within one profile we have different properties. For example, the internal webs have a different property than the outside surfaces, which means that at every intersection line between these webs and the outside surfaces, Limit will detect welds, and this will lead actually to much too many welds. And just to give you an idea what this would look like, these are the welds Limit detected in the structure when using the default settings. So obviously this is much too much, and we have maybe only 4 to 5 longitudinal welds running through the sidewall panels, and not 50 or 100 welds. Yeah. So what can we do about this? This is why we use what we call the profile sets, which means that you can define profiles in Limit, and then Limit will not generate welds within the profile. Yeah, so I will demonstrate this in a manual way. So I will select these elements here, the yellow ones, and here again the yellow ones. And the same down here. And here again. And the same for this side. And I will store these elements, and what you need is a certain prefix. So here we are, and I will store these elements as prof for profiles underline. I will call it side underline 1. And then I can hide these elements, and I can store the remaining elements as create set prof underline side underline 2. And now let me activate both sets, prof1, prof2, show. And if we run the weld generation algorithm once more, then we will get a different result. Generate weld sets by properties. Okay, so again, this will take a few seconds. And now what will happen is Limit will generate the welds, all the welds based on the different properties, and then all the welds that are located within one profile set, they will be deleted. So at the end of the day, only welds that combine different profiles are valid welds and remain, which will cut down the number of welds to let's see, 1, 2, 3, just a couple welds. So those are the welds that we're interested in, and so that's the first step in the preparation of large models, is to define these prof sets, and these prof sets simply are element sets with the prefix prof, and you can generate them in your preprocessor and import them into limit, or select them within limit. A very nice method to do so is to have exclusive properties for each profile, because then you can simply mark an element and select these elements by property ID. So for example, if you click in here, you could say selection by property, and then all the elements of this property would be selected. So this is a nice possibility to do so. Okay, now I will delete these welds once more, and I will import my prof set L-sets, because I don't have time to generate these prof sets manually. So I will import these predefined sets using a file, and this is the profile sets without side panels. And so I have a large number of prof sets here that actually define all the extrusions in the complete model. So if I show all the rest of the model, I have here these prof sets, and as you can see, the whole car body actually is highlighted. So those two, side 1 and side 2, I generated manually, and all the others were imported from a file that we prepared in advance. Okay, so that's the first step, to identify these profiles. There is another possibility to generate welds not based on the property sets but based on part information, but this is a topic that will be covered in a different presentation. Okay, so we have the first step, and now we can generate the weld sets by properties. This will take a few seconds. Now again, limit will search for all the welds where nodes are connected to elements with different properties, and then all the welds that have elements from only one profile will be deleted, and the remaining welds are the ones that actually really connect the extrusions. And besides generating, or besides identifying the location of the welds, limit will also run the welds through the topology classification, or topology filtering as we call it, and it will check which welds are T-junctions, which ones are butt welds, corner weld types, overlap welds. So we're actually here in this phase, and now we are finished, and what we get is here a whole list of weld sets. And those are all the welds we need. Those are the welds that really connect different profiles. So it's actually not so many welds on these aluminum car bodies with extrusions. Okay. Now, next step is to define what kind of weld quality or weld type we would like to use, or which code we would like to use. So I will move to the setup definition. I will skip the loads for the time being, and I will return to the loads, but let's move to the setups first. So I will open up the setup manager, and a new feature in Limit is actually this auto creation. In the old version of Limit 2017, there was the auto creation already, but actually this auto creation method only used a simple default setting, and the new version has more capabilities. So let me explain what the basic idea is. Here, what you can see here is the topology code of each weld set. And the topology actually defines what kind of weld we are looking at. B stands for butt weld. And these numbers actually define the shell normal orientation. So identical topology codes mean that the welds, or actually the elements connected to this or involved in this weld, they have exactly the same orientation in space. And we have different types of welds. B is the butt weld type. C is what we call a corner weld, which means two element rows or two sheets are connected. Then we have what we call the edge welds, which are usually like a profile or some kind of bent or parts of some sections and an attached sheet. Then we have G, which is like a general shape that was not classified. O is overlap situation, and P are profile welds. And there's something special about the profile welds. The profile welds can also have like these internal webs, like this one here in this small icon. And Limit can detect these internal webs and will apply some base or parent material parameters to the inside webs. And last but not least, one important weld type is the T-junction. So here are all the T-welds. And the first step here is actually to select the code you want to use for the assessment. So in our case, let's use the DVS 1608, which is the aluminum is an aluminum code for railway structures. And Limit 2019 has predefined setups for different welds. And within this auto create menu, you can actually define how you want to, or which default settings you want to apply. Okay, which means all the T-joints down here will automatically use the definitions of this one-sided fillet default setting. So what do these default settings look like? If you move to the installation directory of limit, then you will find the setups library directory, and within this setups library you will find subfolders with the name of the codes. And if you move on and then switch to Weld, then you will find a whole list of text files that actually define um, the parameters that will be used. Yeah, so if we want to take a look at the one-sided fillet weld, which is the last one here, then you will see all the parameters, beginning with the throat dimension, which is 70% of the local thickness, and some material parameters, and so on and so on. You are invited to modify and change this as you need it. You can also change the notch case definition, or you can define your own setups, store them, and use them here in order to have them applied to, for example, here all the T-joints. Yeah? So the basic idea is we have a standard setting for T-joints, we have a standard setting for the corners and for profiles. So the T-joints are one-sided fillet welds, and for example the profiles usually are full penetration welds, and that's why we use an HV type of setting for the profiles. Now, in cases where we don't know how the shell normal of the attached sheet actually is oriented, because for a single-sided fillet weld in such a global quick assessment, or in the first loop, we don't have time to check every single fillet weld in the whole structure. So just to make sure that the assessment is conservative, we can tell limit to check both weld orientations, both possible weld orientations, which means check if it's welded only from the top side, and please check also if it's welded only from the bottom side, and give us the relevant result, which means the result with the higher degree of utilizations. We don't need these checks for profiles or for corner or edge welds, because in this case limit has topology information and can automatically orient the weld symbol in the correct way. But we do use it for butt welds, for example, or also for overlaps. Okay, so next step is simply to mark all the elements, all the weld sets here, and to simply hit the auto create button. Let me check, code is okay. And now we have generated some default welds. And one major difference to limit 2017 is that here the status of all welds is set to edited, because we have very reasonable settings. They are maybe a bit conservative for the first approach, but they make sense. They take into account the orientation of the weld and the topology of the weld, and we can continue and run the job. If you would like to check the welds with respect to the orientation of the weld symbol, you simply mark all the welds here and say, okay, I want to see the weld symbol. We can increase the density by not only plotting the symbols at the beginning and the end of the welds, but also in between. Let's say every fifth element. Then I will use the refresh symbol. And now we can take a closer look and see if we can see any symbols here, for example. Here. Okay. So here's, for example, this butt weld seems to be welded from the wrong direction, but for the first approach we had this tick check butt welds welded from both sides, so we are fine. Here you can see the typical profile weld. We have the attached component, and here we have a horizontal and a vertical element for the profile. And maybe let's take a look here. Again, this is a profile set, yeah, as you can see here. We have the profile is here, and here is another profile. So the attached sheet is this horizontal sheet. Here we have a full penetration weld, and we have base material here on the inside, and the weld cross section will be checked here on for the blue element. So especially for these profiles joining the extrusions, this algorithm works very well, and actually you can save a lot of time using this auto creation feature of limit. Okay, so we can close this. We have defined a large number of setups, approximately, I don't know, probably up to 100 welds in just a few minutes. And we can close this. What we need to run a job is we need some loads, and I will open the load manager. I discussed the loads in the beginning. We have two load cases which will be imported from the OP2 of the Nastran analysis, and I will call the first one load case 1, and it was calculated as subcase 1, and then we have a second one, load case 2, LC underline 2, with the subcase number 2. And we have a few combinations. We need some loads to run the assessment, at least 2 loads. But we have here 2 different types of loading, and we will combine these to find the most unfavorable load combination for this structure. And I will do this by defining the loads from text. So in this version you can simply define one load per line, and the syntax actually is listed here. So you start with the load name, load underline 1, then you can define a name for this load group. I will simply call it default. And then you start listing the finite element result name, which is LC underline 1, and you give what we call a weighing factor. In my case, this is a 0.4. So the stress result of load case 1 will be multiplied with 0.4, and then we have a second load finite element result, actually LC2, and we want to use, in this case, 100%, which is a factor of 1.1. So this defines like a linear combination of those 2 load cases, and now I will simply copy these lines. I will rename the loads, and I will simply change the weighing factors. So we have 0.4 and 0.8. So we have like 40 and 80% of load case 1, which will give us a certain vertical dynamic. And then we have the sidewall pressure, which has values from 1 down to minus 0.5. Yeah. These loads are not realistic loads. It's simply to generate or to demonstrate the way to define loads and load combinations within limit. Yeah. So each load here is a sum of stress results multiplied with factors or weighing factors. Okay, now we have 4 load cases here. When limit runs the assessment, then we have 2 searching methods in limit. The first one is simply running through all the loads in a linear way and looking at each load case only once, storing maximum and minimum contributions for each stress component relevant for the weld. And the other possibility is to generate all possible load case pairs and do independent endurance limit analysis for each possible load case pair. So we would run an extra analysis for load 1 against load 2, load 1 against load 3, load 1 against load 4, and so on. So these are the 2 different approaches. The first one is fast and conservative in a way that we combine all maximum stress contributions over all load cases, and we assume that they can occur at the same time. Yeah. So this is actually the point. And down here we can define spectra, which means we could define load cycle numbers, or define rainflow countings. So this down here is usually used for variable amplitude fatigue assessments, but for my example, I don't want to go into further details. Okay, so we have weld sets, we have setups, we have loads, and the next step actually is to define the job. Here you can define the number of CPUs, and using the create button, I'll call a job 1, no, job DVS 1608. Loop 1. Okay, and now we have to define a few parameters and settings. First of all, we have to define which solver was used. In this case, it's Nastran, and we want the English version, which means we want an English output. We will use the HDF5 file, which is the new output file format for limit 2019. You can still use the Geo format, but default is H5. Here we have to select the OP2 file. Then we can choose which type of search criteria we want to use. Critical load case pair is the pairwise search over the load cases, rather than running through all the loads and gathering max min. So I will use the critical load case pair approach. Here I will select all the setups we have defined. I will move them to the right side. Here I can define if I want a fatigue analysis or a static, but this is fine. And we will select the loads. And off we go. Let's take a look at the command window. So this is the echo from the limit solver, and we are in the phase of importing the result data of the OP2. Now the solver started to, actually it switched to four threads or 4 CPUs, and now it's running through all the welds, and this will take a few seconds. The points listed define how how many percent of each element set have been processed, which means each attached element set has 10 points. So usually sets with 2 element rows involved have 20 points. And after limit has assessed all elements, limit will generate text output for the critical elements of each weld. So we're actually here in this phase where limit generates a detailed information for the element with the highest degree of utilization for each weld. Okay, and we are finished. And simply by marking this line and clicking on View Result, we can load the results into Limit Viewer. Okay, here we are. The viewer itself is very similar to Limit CIA, but has a reduced functionality. I will switch to a feature edge view, and then actually you have the results listed here. And the most interesting result actually is the maximum degree of utilization. And EL means that the element or all elements are completely colored with the value of the highest degree of utilization that occurs at one node of the element. It looks pretty much blue, but if we take a look at the legend, we can see that the maximum is 4.83. So actually everything, all values above 1 are not feasible. So I will change the legends to the standard settings I like to use, which means that everything above 1 will occur in a more shocking color magenta, and so we can see different areas that are high loaded and might be a problem. So we have here at the car body end, and up here in the corner we have increased values, and here probably due to the boundary conditions that were applied here, we have some numerical peak stresses in this area, but this here might be interesting. So we have problems here where the side walls are welded to the door posts. So there's a bit going on in the structure. Now if we want to have more detailed information, we can use the query function and click on an element, and for example here it should be possible to see which loads are responsible. So we have load 1 and load 4 that is responsible for this increased degree of utilization. The value is 1.04, so we're actually only 4% above the feasible value. And we have a problem in the point P2, which means in the root point. So if you're not so much familiar with these names or naming conventions of limit, let me explain in a few seconds or minutes. We have assessment points, and these assessment points refer to different positions on the weld. So P1 and P4 are actually toe points, and 5, 6 are toe points as well, and 2 and 3 are actually the root points. And here in the model tree listed in the results, you have results for each assessment point. So the degree of utilization P1 is the root if the structure no, the toe, if the structure was welded from the bottom side. So we can see these are the toe results. Maybe I should toggle the max visibility value. So the worst toe point on a weld section has a degree of utilization of 1.59. Then here the root point, the maximum value is 583. P3 again is a root point, and so on and so on. Those are the different positions. 5 and 6 are actually toe points in the parent material. So here the highest degree of utilization is 165 on the bottom side and 173 on the top side. Yeah. Here basically due to some load or boundary condition effects. Maybe also interesting are the degrees of utilization with respect to the orientation of the weld, which means degree of utilization for the longitudinal stresses. Why do we list these values? Well, if you have a problem with longitudinal stresses, then this is bad news, because then the stresses are too high in an overall sense, because the welds have the highest strength parameters for this longitudinal loading direction, and if the stresses are too high, then you simply have to change the design. Also interesting, or mainly interesting, is the transverse direction, and if you have a problem in the transverse direction, you might have the possibility to change the weld design simply by changing, like, let's say, a one-sided fillet weld to a double-sided fillet weld. And then shear usually is not a big problem. So here in this case, all our problems occur in the lateral or transverse direction, and so we might have a chance to fix it by changing the weld quality, for example. Now, if you're interested in how, for example, the worst weld was defined in limit CA, you can move to the setup manager here. You could sort your welds according to the degree of utilization, and then you simply double click this one weld you're interested in, and limit will open up the edit setup window, and will present what the weld looks like, and it will also present the results. Okay, so it's a one-sided fillet weld, and that's probably a reason for the high degree of utilization. So we could, for example, move back to limit CIA and change this weld design. Yeah? So that's something I would like to show. So if I move back to limit CIA, again here I can open up the setup manager. I can load the degrees of utilization for this last analysis, loop 1. And I can sort my setups according to this loop, and then I can switch to this specific weld setting by simply clicking the edit, and then I can look how and where this weld is positioned. Yeah. So zoom once more. And for example, we want to use, okay, let me see, probably it's welded from, it's not so simple to really see, welded from the outside, but maybe a full penetration situation, so I can import a different setting from the library, for example an HYT nominal. Yeah, so this should improve the weld situation, and with apply I can close this. Yeah. Now it's maybe difficult if you have many welds to keep track of the ones you have changed and the ones you haven't changed yet or checked yet. So in this case, what I would do, I would, for example, go through all the welds with a degree of utilization above 1. Yeah? So I would mark them here, and then I can go to the plugins folder, and I would change the setup status. I would change the status to none, and then I can color these welds by setup status, and the none welds are shown in red. Yeah. For example, the one I just modified. So if I mark this element and look at this element, this weld once more, and I simply apply the settings, then automatically this weld will be set to edited. Yeah? So this way you can simply mark your welds you want to look at and go through, and then doing so, Limit will automatically change them back to edited. Okay. In order to run the job, only edited welds are permissible, so you have to change this back to edited if you want to run the analysis. So I will change the setup status to edited again. Okay. Yeah. So what else would be interesting? We have defined the structure. We have generated results for a first loop, and maybe we have added a second or a third loop, and all the degrees of utilization are within a permissible range. So we would like to document our work, and the documentation can be performed in an automatic way within Limit, because we have what we call a report generation tool. The first step in generating a report actually is to define a view setting in which you want to present the model in your report, and you simply actually move or rotate your structure in a view that you like, or that is good for the report, and then you move to the options, open the view manager, and you simply save the current view. You can define a name. I will call it a report view. Okay, so that's the first step, and then we move to the report manager. We simply create a report for DVS 1608, and in my case this is loop 1, and you have to select a job. Now the job holds all the information. We have definitions of the loads, we have the definition of the welds with their position in the structure, as well as the weld geometry, the codes, notch factors or FAT classes, whatever. And so that's the basis of the report is a job. And then you can define which results you would like to visualize in the report. In my case, I would like to use the utilization, the max degree of utilization, and then we can define the density of weld symbols shown in the viewport. We can define the legend. Let's start from 0.4 to 1. So we can save a blue color of the printer, and here we can choose the report view, which will be used to show all the different weld positions and setups. White backgrounds for figures, yes. Create documentation only for setups with figure sets. Create individual weld symbol figures for setups. Show max value, min for safety, yes. And now we can define the pictures we want to use. From my point of view, this model highlight transparent actually is a good way to show the general, the global location of the weld within the structure. So I usually use this as the first picture. Excuse me, wrong button. Here, model symbol model highlight transparent, and we don't want to use a fit to view because we want to have the overall picture. Secondly, I will use the mode plus symbol plus highlight transparent, which is here, and then I need some results. And for the last two, I would like to zoom in as good as possible. Okay, now this generating the report will take a few minutes. So I have already prepared the report. So the report for this will run like for 7 to 8 minutes, and I don't want to wait that long. So let me switch directly to the report. I have generated just prior to this presentation demos, and here you have the possibility of generating a report as an HTML, or with Tech or LaTeX you can generate a PDF. Let me open up the HTML file. Okay. That takes a few seconds. Yeah, here we are. So that's what the report looks like. It gives you information on the job, on the loads, and then you get a overview of the degrees of utilization in the structure, and then the detailed information for each weld. So what does it look like here? This is the job explanation, description. Here the load definition, including the name of OP2. Then here the linear combinations of the loads. And then we have here the list of degrees of the maximum degrees of utilization per weld, and here actually the links or shortcuts directly to these areas where the weld is located. So as pointed out earlier, this is actually really a nice view where you can see where the weld is located, and then you can see here the parameters for the welds here, for example the geometry and the material settings, the cross section, it's a one-sided fillet weld, and here the notch cases for the weld F2 for the root position, and the degrees of utilization for each point, and the maximum here is the 5.83, and then the degree of utilization here of the structure, and so on and so on. So this will be repeated for each weld in the structure, and so this is a very convenient way to document. Sometimes the view is maybe not perfect, but you can define individual views for each setup. Within the edit setup module, you can define views for the report generation, and so you can also add some specific views for setups. Okay, so actually I'm finished with all the points I was planning to discuss. Thanks for your attention. I hope you liked the information and the new features. I think especially the auto creation in combination with the topology, filtering, and the new predefined weld settings are very useful, especially for a first quick approach or first quick assessment of the structure, and using these color status views. It's even simple to go through the structures in a second loop and really focus on critical welds without losing the overview. So I think Limit 2019 is, with respect to efficiency in large structures, much better than the 2017 version. And yeah, so please check out the new features, and we will be happy to hear feedback. And once more, thanks for the attention and have a nice day.